Some nights the sky feels older than it should. Stars breathe light that left home before your great-grandparents were born. Time folds. Distance becomes memory. Maybe that's just the universe whispering to itself. You've looked up before. Everyone has. But tonight let's look differently. Not as observers, as participants. Because every atom in your body was forged inside a star that died long before Earth existed. You are made of the same dust that swirls in the Milky Way's arms. The calcium in your bones, the iron in your blood, the oxygen you just inhaled, all born in stellar furnaces billions of years ago. Carl Sagan once said, "We are a way for the cosmos to know itself." He wasn't being poetic. He was being precise. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell not for noise, but so the next quiet night can find you again. Now, let's drift. Tonight we'll wander through the universe's deepest secrets, not the loud ones, the quiet ones, the kind that physicists whisper about in late-night conversations. Things like light that moves but never ages. Matter you can't see but holds galaxies together. Waves in the fabric of space itself. You don't need to understand everything. Just rest and let curiosity do the listening. Light moves fast. You know this. But fast isn't the same as instant. When you look at the sun, you're seeing it as it was 8 minutes ago. That's how long light takes to cross 93 million miles. The sun could have vanished 8 minutes ago, and you'd still see it shining. Still feel its warmth on your skin, still assume everything was fine. Scientists measure cosmic distances. In light years, the distance light travels in 1 year. Proxima Centauri, our nearest star neighbor, is 4.24 light years away. Look at it tonight, and you're seeing light that left when you were 4 years younger. The Andromeda Galaxy, our nearest galactic neighbor, is 2.5 million light years distant. Its light began traveling toward Earth before Homo sapiens walked upright, before tools, before fire. That photon journeyed through empty space while our ancestors were still figuring out how to survive the African savanna. You're not just looking at space, you're looking at time. Astronomers call this look-back time. The deeper we peer into the universe, the further back we see. The Hubble Space Telescope captured images of galaxies 13.4 billion light years away, meaning we see them as they were just 400 million years after the Big Bang. Infant galaxies, the universe in its childhood. Some of those galaxies no longer exist. They've collided, merged, and been torn apart by gravity. But their light kept traveling, a photograph of something that died eons ago. Here's the strange part. Light doesn't experience time. Einstein's theory of relativity tells us that as you approach the speed of light, time slows down. At light speed, time stops completely. A photon leaving a distant star doesn't feel the journey. From its perspective, emission and absorption happen simultaneously. It's born and dies in the same instant. But from your perspective, watching from Earth, that photon traveled for millions of years. Time is relative, not metaphorically, literally. NASA's Voyager 1 spacecraft, launched in 1977, is now over 15 billion miles from Earth. Messages sent to it take more than 22 hours to arrive. If aliens lived on a planet orbiting Proxima Centauri and sent us a radio signal today, we wouldn't receive it until 2029. And if we replied immediately, they wouldn't hear back until 2033. Conversations across the cosmos happen in slow motion. You've probably heard that the universe is expanding. But what does that actually mean? In 1929, astronomer Edwin Hubble noticed something odd. Distant galaxies weren't just moving away from us, they were moving faster the farther they were. A galaxy 10 million light years away receded at a certain speed. A galaxy 100 million light years away receded 10 times faster. This wasn't because galaxies were flying through space. It was because space itself was stretching. Imagine dots on a balloon. As you inflate it, The dots move apart not because they're moving, but because the surface between them is expanding. The universe works the same way. Galaxies aren't racing away from each other. The fabric of space is growing. Scientists measure this expansion using the Hubble constant, roughly 70 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space expands by 70 kilometers every second. The universe is currently 93 billion light-years in diameter, but it's only 13.8 billion years old. How can it be wider than its age suggests? Because space itself has been expanding faster than light can cross it. Nothing with mass can move faster than light, but space doesn't have mass. It can stretch as fast as it wants. Some galaxies are moving away from us faster than light speed. We will never see them no matter how long we wait. Their light is being carried backward by the expansion of space, like a swimmer fighting a current stronger than their stroke. There are edges to the observable universe, not because the universe ends there, but because light from beyond those edges hasn't had time to reach us yet. Every second, the observable universe shrinks not in size, but in content. Galaxies slip beyond the cosmic horizon, pulled away by expansion. In trillions of years, future astronomers won't see distant galaxies. They'll look out and see darkness. They might conclude they live in a lonely, empty cosmos. They'll be wrong, but they'll have no way to know. Right now, you live in a rare era. The universe is old enough to have formed stars, planets, and life, but young enough that light from distant galaxies still reaches us. You exist in a cosmic sweet spot. The universe is 13.8 billion years old. Humans have existed for 300,000 years. Civilization for 10,000. You for a handful of decades. And yet you're here, looking up, wondering. Light carries memory. Space carries time. And somewhere in the quiet folds of the cosmos, a star is dying so that new ones can be born. Gravity doesn't pull, it bends. Einstein figured this out in 1915, sitting alone with equations that most people thought were beautiful nonsense. He said, mass warps space-time the way a bowling ball warps a trampoline. Planets don't orbit because invisible strings tug them. They're following curves in the fabric of reality itself. You can see the proof on any GPS screen in your pocket. Satellites orbiting Earth experience time differently than you do. They're moving fast, which slows their clocks down slightly, about 7 microseconds per day, according to Einstein's special relativity. But they're also farther from Earth's mass, where gravity is weaker, which speeds their clocks up by about 45 microseconds per day. The net effect, 38 microseconds faster each day. That doesn't sound like much, but GPS needs nanosecond precision to calculate your position. Without correcting for relativity, without accounting for the fact that time itself runs at different speeds, depending on where you are and how fast you're moving, your navigation would be off by several miles within hours. Einstein's equations aren't philosophy. They're inside every phone, every car, every plane. In 1919, astronomers waited for a solar eclipse. They wanted to photograph stars near the sun's edge to see if their light bent as it passed through the sun's gravitational field. The stars appeared shifted from where they should have been, exactly as Einstein predicted. Newspapers around the world announced, "Lights all askew in the heavens." Light doesn't travel in straight lines through the universe. It follows the shortest path through curved space. When something massive sits between you and a distant light source, the light bends around it. Astronomers call this gravitational lensing. The Hubble Space Telescope has captured images of entire galaxies smeared into rings and arcs. Light from objects 10 billion years away, bent and magnified by galaxies in the foreground. In 2022, the James Webb Space Telescope photographed a galaxy cluster called SMACS 0723. The image shows dozens of distorted galaxies, their light stretched into crescents and loops by the cluster's immense gravity. You're looking at light that's been folded by the universe itself. Some lensing events create perfect circles, Einstein rings. Light from a background galaxy passes around a foreground galaxy in all directions, at once forming a glowing halo. It's rare. The alignment has to be almost exact. But when it happens, you see geometry made from starlight. Have you ever wondered what holds galaxies together? In the 1970s, astronomer Vera Rubin measured how fast stars orbit in spiral galaxies. She expected stars at the edges to move slower than stars near the center, the same way Neptune orbits more slowly than Mercury. But that's not what she found. Stars at a galaxy's outer rim move just as fast as stars near the core. By every calculation, those outer stars should have been flung into space long ago. Something invisible was holding them in place. Rubin once said, "In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge." She was right. About 85% of the universe's mass doesn't emit light, doesn't absorb it, doesn't interact with ordinary matter in any way we can easily detect. Scientists call it dark matter, though invisible scaffolding might be more accurate. You can't see it, can't touch it. But without it, galaxies would tear themselves apart. Researchers have built detectors deep underground, shielded from cosmic rays and radiation, waiting for a single dark matter particle to collide with an atomic nucleus. So far, nothing definitive. Dark matter is so weakly interacting that trillions of particles might be passing through your body right now and you'd never know. Some think it's made of WIMP's weakly interacting massive particles. Others suggest Axions theoretical particles 1,000,000,000 times lighter than electrons. Some wonder if we've been wrong about gravity all along, if there's a modification to Einstein's equations we haven't discovered yet. The universe is held together by something we can barely prove exists. Humbling, isn't it? When a massive star exhausts its fuel when fusion stops and there's nothing left to fight. Gravity's crush, the core collapses. Electrons and protons are squeezed together, forming neutrons. What's left is a sphere about 20 kilometers across, roughly the size of a city, but with more mass than the sun. A neutron star. A single teaspoon of neutron star material weighs about 1,000,000,000 tons. If you could bring that teaspoon to Earth, hypothetically and possibly, it would punch straight through the planet's crust and fall toward the core. Neutron stars spin, fast. Some rotate hundreds of times per second. Their surfaces move at a significant fraction of light speed. As they spin, they emit beams of radiation from their magnetic poles. When those beams sweep across Earth, we detect a pulse regular as clockwork. That's why we call them pulsars. The first pulsar was discovered in 1967 by astrophysicist Jocelyn Bell Burnell. She was a graduate student at Cambridge analyzing radio telescope data. When she noticed something odd, a signal that repeated every 1.337 seconds, precise beyond anything natural they'd seen before. For a brief moment, the team wondered if it might be an alien transmission. They nicknamed it LGM-1, Little Green Men. 1. It wasn't aliens. It was a dead stars. 2,000 light years away, spinning in the dark broadcast radio waves like a cosmic lighthouse. Millisecond pulsars spin even faster, over 700 times per second. They're more stable than atomic clocks. Some deviate by less than a microsecond over decades. NASA's NICER mission studies these objects, hoping to use them as natural navigation beacons for deep space travel. Future spacecraft might find their way using pulsar signals the way ancient sailors used stars. You could set your watch by a dead star, but neutron stars aren't the strangest objects gravity can create. If a dying star is massive enough, more than about 20 times the sun's mass, its core doesn't stop collapsing at neutron density. It keeps going. Neutrons can't resist. Nothing can. The core collapses into a point of infinite density surrounded by a boundary called the event horizon, a black hole. Black holes don't suck. That's a misconception. They don't reach out and grab things. If the sun suddenly became a black hole right now, magically and possibly Earth would keep orbiting exactly as it does. Same mass, same gravity, same orbit. What makes black holes strange isn't their pull, it's the boundary. Cross the event horizon and you can never leave. Not because gravity is pulling you back, but because space-time itself is curved so steeply that all paths, every possible direction, you could move point inward. Light itself can't escape. Not because it's being yanked, but because there is no outward anymore. Imagine watching a friend fall toward a black hole. As they approach the event horizon, they'd appear to slow down. Their clock would tick slower compared to yours. Light from them would stretch toward longer wavelengths, red shifting into infrared, then radio waves, then nothing. They'd freeze at the edge, never quite crossing. Eventually, they'd fade from view. But from their perspective, nothing unusual happens. They cross in finite time. No barrier, no wall. Just a one-way threshold into a region of space-time they can never leave. Time behaves differently depending on where you stand. Stephen Hawking predicted that black holes aren't entirely black. Quantum effects near the event horizon allow them to emit faint radiation, now called Hawking radiation. Over trillions upon trillions of years, black holes slowly evaporate. The smaller they get, the faster they radiate until eventually they vanish in a final burst of energy. Even black holes die. It just takes longer than the current age of the universe. Gravity shapes time, mass bends space. Light remembers everything it passes through. Most of what exists doesn't want to be seen. You're surrounded by it right now. It's passing through your skin, through the chair you're sitting in, through the walls of your room, through the entire planet. Trillions of particles every second, invisible and silent, holding the cosmos together without ever saying hello. Dark matter makes up about 85% of all matter in the universe. Everything you can see, stars, planets, galaxies, light itself, is just the leftover 15%. We are the minority, the exception. The visible dust floating in an invisible ocean. Scientists didn't go looking for dark matter. They stumbled into it by noticing something was wrong with the math. In 1933, Swiss astronomer Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. He measured how fast those galaxies were moving. Then he calculated how much mass the cluster needed to hold them together at those speeds. The numbers didn't match. The galaxies were moving far too fast. By his calculations, they should have been flung apart billions of years ago, but they weren't. Something invisible, something with mass, but no light was holding them in place. Zwicky called it Dunkel Materie, dark matter. Most astronomers ignored him for decades. Then came Vera Rubin. In the 1970s, Rubin studied spiral galaxies, measuring how stars orbit around galactic centers. She expected the same pattern we see in our solar system. Inner planets move faster. Outer planets move slower. Neptune crawls compared to Mercury. That's how gravity works when most of the mass is concentrated in the center. But galactic rotation curves were flat. Stars at the edge of a galaxy move just as fast as stars near the core. It made no sense. Unless there was something else, something massive and invisible extending far beyond the visible galaxy, wrapping it in a halo of unseen matter. Rubin spent years confirming the pattern. Galaxy after galaxy, the same result. She once said, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined." She was describing dark matter. But what is it? That's the question physicists have been trying to answer for 50 years. They know dark matter exists because of its gravitational effects. They can measure how it bends light, how it holds galaxies together, how it shapes the large-scale structure of the universe. But they can't see it, can't touch it, can't detect it directly. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic forces at all. It only responds to gravity. It's like trying to study a ghost by watching doors open and close in an empty room. Some scientists think dark matter is made of WIMPs, weakly interacting massive particles. These would be subatomic particles with significant mass, but almost no interaction with ordinary matter. Billions could pass through your hand every second without ever hitting a single atom. Others propose Axions theoretical particles 1 billion times lighter than an electron swarming through space in vast clouds. Some researchers wonder if dark matter isn't particles at all. Maybe we've been wrong about gravity. Maybe Einstein's equations need a small correction, something called modified Newtonian dynamics, or MOND. Maybe there's a force we haven't discovered yet that makes gravity behave differently at galactic scales. But most evidence still points to particles, invisible, untouchable everywhere. Deep underground in abandoned mines and tunnels, scientists have built some of the most sensitive detectors ever made. These experiments, like Xenon 1T in Italy or the cryogenic dark matter search in Minnesota, sit beneath millions of tons of rock to shield them from cosmic rays and background radiation. They're waiting for a single event, a dark matter particle colliding with an atomic nucleus. The detectors use supercooled liquid xenon, or ultra-pure germanium crystals. If a dark matter particle hits a nucleus, it would produce a tiny flash of light or a minuscule vibration, barely detectable but real. Teams of physicists watch the data year after year, searching for that signal. So far, nothing conclusive. But absence of evidence isn't evidence of absence. Dark matter might interact so weakly that even these incredibly sensitive instruments aren't enough. Or maybe we're looking for the wrong thing in the wrong way. Have you ever thought about how strange it is that we know something exists but can't find it? It's like knowing someone is in the room with you because you can hear their breathing, feel the warmth of their presence, see the way objects move around them, but you can't see them at all. You know they're real, you just can't prove it the way you'd like. The universe is full of things like that. Dark matter isn't evenly spread. It clumps. It forms halos around galaxies, vast spherical clouds that extend far beyond the visible stars. Our own Milky Way is embedded in a dark matter halo roughly 10 times wider than the galaxy itself. We're swimming through it right now. Computer simulations of cosmic structure can't work without dark matter. When physicists model the universe's evolution, starting from the Big Bang and moving forward, they can only recreate the web-like structure of galaxy clusters if they include dark matter in the equations. Without it, galaxies don't form properly. The universe looks wrong. In 2006, astronomers observed 2 galaxy clusters colliding in an event called the Bullet Cluster. When the clusters smashed together, their visible matter, mostly hot gas, slowed down and piled up in the middle, glowing in X-rays. But the gravitational mass, measured by how the collision bent light from background galaxies, passed right through, barely interacting. The visible matter and the gravitational mass separated. It was one of the strongest pieces of evidence that dark matter is real and distinct from ordinary matter. NASA called it direct proof that dark matter exists. The matter that doesn't interact with light didn't slow down when the clusters collided. It kept going ghost-like, unaffected. Dark matter shapes the universe without ever appearing in it. The cosmic microwave background, that faint glow of radiation left over from the Big Bang, carries an imprint of dark matter. The tiny fluctuations in temperature across the sky show where dark matter clumped together in the early universe, pulling ordinary matter into those same regions, eventually forming the first stars and galaxies. Dark matter was the seed. Everything visible grew from its invisible foundation. In a way, we owe our existence to something we can't see. If dark matter didn't exist, galaxies wouldn't have formed, stars wouldn't have ignited, planets wouldn't have coalesced. The atoms in your body forged in stellar cores scattered by supernovas gathered into a new solar system wouldn't be here. You wouldn't be here. You're made of stardust. But that stardust only exists because of the invisible scaffolding holding everything together. Some nights when you look up, you might notice how much space there is between stars, but it's not empty. It's full of something we can't name, can't touch, can't see. Something ancient, something patient, Dark matter doesn't ask to be understood. It just holds the universe together quietly without recognition. There's a glow in the sky you can't see with your eyes. It's everywhere. Above you, below you, in every direction you could point. Older than stars, older than galaxies, older than anything with shape or structure. A faint whisper of light from when the universe was young and simple and almost impossibly hot. Scientists call it the cosmic microwave background, the oldest light in existence. If you could see microwave radiation the way you see visible light, the entire sky would glow with a soft, uniform warmth. Not bright, not dark, just present. A low hum of ancient photons that have been traveling through space for 13.8 billion years, cooling as the universe expanded, stretching from visible light into infrared, then into microwaves, arriving at your eyes right now as an invisible bath of radiation. You're standing inside the afterglow of creation. The story begins 380,000 years after the Big Bang. Before that, the universe was too hot for atoms to exist. Protons and electrons couldn't stay together. They'd form briefly, then get blasted apart by high-energy photons. The entire universe was a dense, glowing plasma, opaque, like trying to see through fog made of light itself. But as the universe expanded, it cooled. Eventually, it reached a temperature around 3,000 Kelvin, hot enough to glow like the surface of a red star, but cool enough for electrons and protons to finally bond into stable hydrogen atoms. This moment is called recombination, when atoms formed photons could suddenly travel freely. Before recombination, light couldn't move more than a short distance without hitting an electron and scattering. After recombination, space became transparent. Light that had been trapped was released all at once, flooding outward in every direction. That light is still traveling. It's the cosmic microwave background. The first light that could move freely through the universe, now redshifted and cooled to just 7 Kelvin above absolute zero. It's not light from a star or a galaxy. It's light from the universe itself, from a time before stars existed. You're seeing a photograph of the infant cosmos. In 1964, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate noise from a radio antenna. They kept detecting a persistent hiss, a faint signal coming from every direction in the sky. They checked the equipment. They cleaned out pigeon droppings from the antenna. Nothing worked. The signal wouldn't go away. They didn't realize they'd discovered the edge of the observable universe. Physicists Robert Dicke and Jim Peebles, working at Princeton, heard about the signal and recognized it immediately. This was the relic radiation predicted by Big Bang Theory light from the early universe, cooled by billions of years of expansion. Penzias and Wilson won the Nobel Prize in 1978 for finding something they weren't looking for. The CMB is almost perfectly uniform. Almost. If you measure the temperature in one part of the sky, it's about 2.725 Kelvin. Measure another part and it's 2.725 Kelvin. Across billions of light years, the temperature varies by less than 1 part in 100,000. The universe at the moment of recombination was astonishingly smooth, but not perfectly smooth. There are tiny fluctuations, regions slightly warmer or cooler than average by just a few millionths of a degree. These fluctuations are crucial. They represent tiny differences in density in the early universe. Regions that were slightly denser had slightly more matter, slightly more gravity. Over billions of years, those denser regions pulled in more matter, growing into the cosmic web of galaxies and galaxy clusters we see today. The seeds of everything visible were planted in those microscopic temperature differences. In 1989, NASA launched the Cosmic Background Explorer satellite COBE to map the CMB in unprecedented detail. The results were stunning. The universe's baby picture showed faint blotches and ripples patterns of slightly warmer and cooler regions. Cosmologist George Smoot, lead scientist on the project, said, "If you're religious, it's like looking at God." He meant the patterns matched Big Bang predictions almost perfectly. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. It spent 9 years measuring the CMB with extraordinary precision, creating a map of the sky showing temperature variations down to millionths of a degree. From that map, scientists calculated the age of the universe, 13.77 billion years, the density of dark matter and dark energy, and the rate of cosmic expansion, all from studying ancient light. In 2013, the European Space Agency's Planck satellite refined the measurements even further. The map Planck produced is the most detailed image of the early universe we have. It shows the CMB as it was 380,000 years after the Big Bang ripples and swirls of temperature variation, each one corresponding to a region of space where matter was beginning to clump together. Every galaxy, every star, every planet, everything you see when you look up at night grew from those ripples. The CMB tells us something profound: the universe had a beginning. Before Kobe, some physicists still wondered if the universe might be infinitely old, cycling through endless expansions and contractions. But the CMB is direct evidence of a hot, dense state in the distant past. The universe was once much smaller, much hotter, and fundamentally different than it is now. You can trace everything back to that moment. The CMB also reveals that space is flat, not curved like a sphere or a saddle, but geometrically flat, meaning parallel lines stay parallel forever. If the universe were curved, the patterns in the CMB would look distorted. They don't. The angles add up exactly the way Euclidean geometry predicts. This flatness is strange. It suggests the universe sits precisely at a critical density, just enough matter and energy to balance expansion without collapsing or flying apart forever. That precision is so fine-tuned, it's hard to explain without invoking something called inflation. A brief period in the universe's first fraction of a second when space expanded faster than light, smoothing out irregularities and setting the conditions for everything that followed. The CMB carries imprints of inflation. The slight variations in temperature match the predictions of inflationary theory almost exactly. Some nights, you might wonder what existed before the Big Bang. The honest answer is no one knows. The CMB is the oldest signal we can detect. It's the edge of what's knowable through observation. Before recombination, the universe was opaque. No light from earlier times can reach us. It's a wall we can't see past. But that wall is beautiful. The cosmic microwave background surrounds you like a sphere of ancient light, marking the boundary between what we can see and what remains hidden. It's not a physical barrier, it's a horizon in time. The farther you look into space, the farther you look into the past, until eventually you reach that moment, 380,000 years after the beginning, when light first broke free. And that light has been traveling toward you ever since. Right now, photons from the CMB are passing through your body. They left the surface of last scattering 13.8 billion years ago, cooled by the expansion of space, and arrived here now at this exact moment. They've traveled farther and longer than anything else you'll ever encounter. The oldest light in the universe is touching you. It doesn't ask to be noticed. It doesn't glow in colors you can see. But it's there, patient and quiet, a memory of the beginning written across the entire sky. The universe is getting bigger, not just growing in the sense that things are moving apart. The space between things is being created. New distance is appearing where no distance existed before. Galaxies aren't racing away from each other. Through space itself is stretching, carrying them along like boats drifting on an expanding ocean. You're living inside something that's growing. For most of human history, people assumed the cosmos was static, eternal, and unchanging. The stars wheeled overhead in the same patterns generation after generation. The universe seemed fixed like a stage where events happened, but the stage itself never moved. Even Einstein believed this. In 1917, when he applied his new equations of general relativity to the entire universe, he found something disturbing. His equations predicted that space couldn't stay still. It would either expand or collapse. Since everyone knew the universe was static, Einstein added a term to his equations, the cosmological constant, a kind of anti-gravity force that would hold everything in balance. He called it the biggest blunder of his life, because the universe isn't static, it's expanding. And we know this because of a man who spent his nights photographing galaxies through a telescope on Mount Wilson. His name was Edwin Hubble. In the 1920s, most astronomers thought the Milky Way was the entire universe. They saw spiral nebulae, cloudy smudges of light scattered across the sky, but assumed they were just gas clouds within our own galaxy. Hubble changed that. Using the 100-inch Hooker telescope, the most powerful in the world. At the time, he identified individual stars within the Andromeda Nebula. Among them were Cepheid variable stars that pulse with predictable brightness. By measuring how bright they appeared versus how bright they actually were, Hubble calculated their distance. Andromeda was 900,000 light-years away, far beyond the edge of the Milky Way. We weren't alone. The universe was full of galaxies, but Hubble's next discovery was even more profound. He noticed something strange about the light from distant galaxies. Their spectral lines, the specific wavelengths of light emitted by hydrogen and other elements, were shifted toward the red end of the spectrum. Red shift. It meant the galaxies were moving away from us. At first, it seemed random, but in 1929, Hubble published a paper showing a clear pattern. The farther away a galaxy was, the faster it was receding. A galaxy 10 million light-years away moved at a certain speed. A galaxy 20 million light-years away moved twice as fast. A galaxy 100 million light-years away moved 10 times faster. This wasn't random motion. This was systematic expansion. Hubble's law states that the velocity of a galaxy's recession is proportional to its distance. Mathematically, it's written as v equals h0xd, where v is velocity, d is distance, and h0 is the Hubble constant, roughly 70 kilometers per second per megaparsec. What does that mean in practical terms? For every 3.26 million light-years of distant space expands by about 70 kilometers every second. A galaxy 10 megaparsecs away recedes at 700 kilometers s. A galaxy 100 megaparsecs away recedes at 7,000 kilometers s. The farther you look, the faster everything moves away. Not because galaxies are flying through space, but because space between them is growing. Imagine dots on the surface of a balloon. As you inflate it, every dot moves away from every other dot, not because the dots are moving, but because the surface they're on is stretching. No dot is at the center. From any dot's perspective, all the others are moving away. That's what's happening to galaxies. You might wonder if everything is moving away from us. Does that mean we're at the center of the universe? The answer is no. Every point in space sees the same thing. An observer in Andromeda would look at the Milky Way and see us receding. They'd look at distant galaxies and see them receding faster. From their perspective, they'd seem to be at the center too. There is no center, or rather, every point is the center. The expansion doesn't mean galaxies are moving through space faster than light. It means space itself is expanding, and distant galaxies are being carried along. Nothing with mass can move through space faster than light. That's still true. But space can expand as fast as it wants. It doesn't have mass. It doesn't have speed in the usual sense. Some galaxies are receding faster than light speed because of the expansion of space itself. This has a strange consequence. There are galaxies we will never see. Their light is being carried backward by the expansion of space, like a swimmer fighting a current stronger than their stroke. The photons they emit toward us are losing ground, stretched into longer and longer wavelengths, red-shifted into the infrared, then into radio waves, then into wavelengths so long they effectively vanish. Those galaxies exist, but they're beyond the cosmic horizon. Unreachable. Hubble's discovery meant the universe had a history. If galaxies are moving apart now, they must have been closer together in the past. Trace the expansion backward and eventually everything converges to a single point, a moment of origin. The Big Bang. Not an explosion in space, but an expansion of space. The universe didn't burst into an existing void. Space and time themselves began expanding from an infinitely dense, infinitely hot state. There was no before in the usual sense, because time itself started with the expansion. Scientists have refined Hubble's measurements over the decades. The exact value of the Hubble constant is still debated. Some measurements give 67 km/mpc, others give 73. The discrepancy is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology. Different methods give slightly different answers, and no one knows why. But the expansion itself is undeniable. In 1998, astronomers made another startling discovery. They were studying distant supernovae exploding stars that can be used as standard candles to measure cosmic distances. They expected to find that the universe's expansion was slowing down, gradually braked by the gravitational pull of all the matter within it. Instead, they found the opposite. The expansion is accelerating. Galaxies aren't just moving apart, they're moving apart faster and faster. Something is pushing space to expand more rapidly over time. Scientists call it dark energy, though no one knows what it is. It makes up about 68% of the universe's total energy. Dark matter is another 27%. Ordinary matter, stars, planets, gas, dust, everything you can see is just 5%. We live in a universe dominated by things we don't understand. Dark energy behaves like Einstein's old cosmological constant, the one he added to keep the universe static. Ironically, the term he called his biggest blunder might have been right after all, just for the wrong reason. The universe isn't static, but there does seem to be an intrinsic energy in space itself, pushing everything apart. The farther into the future you go, the emptier the universe will become. In trillions of years, galaxies beyond our local group will have moved so far away that their light will no longer reach us. Future civilizations, if they exist, will look into the sky and see only darkness beyond their own galactic neighborhood. They might conclude they live in an isolated, lonely cosmos with no other galaxies. They'll be wrong, but they'll have no way to know. You live in a rare moment. The universe is old enough to have formed stars and planets and life, but young enough that light from distant galaxies can still reach us. You can look up and see billions of years into the past across billions of light years of space. That won't always be true. Right now, the universe is expanding at about 70 kilometers per second for every 3.26 million light years. That doesn't sound fast on human scales, but across cosmic distances, it's relentless, unstoppable. The space between you and distant galaxies grows every second. Not because anything is moving, because space itself is being made. Some places in the universe don't let go. You could throw light at them, and the light would fall inward, never to return. You could aim a beam of the fastest thing that exists directly away from them, and it would curve back trapped. Not because of force, because of geometry. Because space-time itself is bent so steeply that every direction points the same way. Down. Black holes aren't holes. They're objects. Incredibly dense concentrations of mass compressed into regions so small that the curvature of space-time around them becomes extreme. They don't suck. That's a common misconception. They don't reach out and grab things like vacuum cleaners. If the sun became a black hole, right now impossible, but imagine Earth would keep orbiting exactly as it does. Same distance, same speed, same path. The gravitational pull would be identical because the mass would be identical, just compressed into a much smaller space. What makes black holes strange isn't their gravity. It's the boundary, the event horizon. Cross that line and you can never come back. Not because something is pulling you, because space-time is curved so severely that all possible paths lead inward. The geometry of reality itself forbids escape. You could fire your rocket engines at full thrust, pointed directly away from the black hole, and you'd still fall inward. Not because you're not going fast enough, because away doesn't exist anymore. Inside the event horizon, all roads lead to the center. Physicist John Wheeler coined the term black hole, in 1967, though the concept is older. In 1916, just months after Einstein published general relativity, physicist Carl Schwarzschild found an exact solution to Einstein's equations describing the space-time around a spherical mass. He was serving in the German army during World War I, calculating equations in the trenches, dying of a rare autoimmune disease. His solution predicted something bizarre. If you compressed enough mass into a small enough space, you'd create a region where space-time curved infinitely, a singularity surrounded by a point of no return. Einstein didn't believe it. He thought nature would find a way to prevent such objects from forming, but nature disagreed. Black holes form when massive stars exhaust their fuel. For most of a star's life, fusion in the core generates outward pressure that balances the inward crush of gravity. But when fusion stops, when there's no more fuel to burn, nothing holds the star up anymore. The core collapses. If the star is massive enough, nothing can stop the collapse. Not electron pressure, which holds up white dwarfs. Not neutron pressure, which holds up neutron stars. The core compresses past every known limit, shrinking toward a point of infinite density, a singularity. The event horizon forms around it like a one-way membrane. Its size depends on mass. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometers in radius. For a black hole with 1 million solar masses, it would be about 3 million kilometers across, roughly 4 times the distance from Earth to the Moon. Stellar mass black holes form from dying stars. But supermassive black holes, millions or billions of times the Sun's mass, live at the centers of galaxies. Our own Milky Way has one. It's called Sagittarius A Dices, and it weighs about 4 million solar masses. You can't see it directly, but you can watch stars orbiting around it, whipping through space at thousands of kilometers per second, tracing elliptical paths around something invisible. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow. The target was M87 Cicel, a supermassive black hole in the center of galaxy, M87 about 55 million light-years away. It weighs 6.5 billion solar masses. The image shows a bright ring of light surrounding a dark circle. The dark circle isn't the black hole itself. It's the event horizon shadow, a region where light is either captured or bent so severely it can't escape. The bright ring is light from gas swirling around the black hole at nearly the speed of light, heated to billions of degrees by friction. That image represents years of data from radio telescopes across the entire planet, coordinated to act as a single Earth-sized telescope. Humanity took a photograph of a shadow 55 million light-years away. Time behaves strangely near black holes. Imagine you're watching a friend fall toward the event horizon. As they get closer, something odd happens. They appear to slow down. Their clock ticks slower compared to yours. Light from them shifts toward red as it climbs out of the black hole's gravitational well. They approach the horizon. Closer, closer, but they never quite cross. They freeze at the edge, moving slower and slower, their image redshifting into darkness as photons stretch into longer and longer wavelengths. Eventually, they fade from view. Not because they stopped, but because their light becomes too dim and too redshifted to detect. But from their perspective, nothing unusual happens. They cross the event horizon in finite time. No barrier, no warning, no sensation. Just a one-way threshold into a region where escape is geometrically impossible. They don't see themselves freeze. They don't feel time stop. They fall. This is called gravitational time dilation, and it's a direct consequence of general relativity. Time runs slower in stronger gravitational fields. Near a black hole, the effect becomes extreme. If you could somehow hover just outside the event horizon of a supermassive black hole, held there by impossibly powerful rockets, and you stayed for 1 hour by your watch, decades could pass on Earth. Time itself bends. Inside the event horizon, things get stranger. At the singularity, the point of infinite density at the center, Einstein's equations break down. They predict infinite curvature, infinite tides conditions, where our understanding of physics fails. Most physicists believe quantum effects must take over at some scale, preventing true infinities. But we don't have a theory of quantum gravity yet. We can't describe what really happens at the center of a black hole. It's one of the few places in the universe where we hit the edge of knowledge. Stephen Hawking showed that black holes aren't entirely black. Quantum fluctuations near the event horizon allow them to emit faint radiation. Virtual particle pairs, matter, and antimatter constantly pop into existence throughout space, then annihilate each other almost instantly. But near a black hole's event horizon, one particle might fall in while the other escapes. To an outside observer, it looks like the black hole is radiating. This is Hawking radiation. It's incredibly faint. A black hole with the mass of the sun would emit radiation at a temperature of just 60 billionths of a Kelvin, far colder than the cosmic microwave background. It would take 10⁻⁶7 years to evaporate. But smaller black holes radiate faster. A black hole the mass of a mountain would glow like a star. A black hole the mass of a car would evaporate in a fraction of a second, releasing the energy of multiple nuclear bombs. In the far, far future, trillions of years from now, Hawking radiation will become important. After all the stars have died and the universe has cooled, black holes will be the last massive objects left. Slowly, imperceptibly, they'll radiate away their mass, one photon at a time, until they vanish. Even black holes die. It just takes longer than the current age of the universe many times over. Physicists debate what happens to information that falls into a black hole. Quantum mechanics says information can't be destroyed. General relativity says anything crossing the event horizon is gone forever. These two ideas conflict the black hole information paradox. Some think information is encoded on the event horizon's surface. Some think it escapes through Hawking radiation. Some think it's lost, and quantum mechanics needs revision. No one knows for sure. Black holes sit at the boundary of what we understand. They're real. We've photographed their shadows, watched stars orbit them, detected gravitational waves from their collisions. But they contain mysteries we can't yet solve. Places where time stops, regions where all paths lead inward, boundaries between the knowable and the unknown. You'll never visit one, but knowing they exist changes how you see the universe. Somewhere out there, space-time is bent so steeply that light itself can't climb back out. When a star dies, sometimes it leaves behind something impossible, a sphere the size of a city, dense beyond comprehension, spinning hundreds of times per second. Surface gravity so intense that if you dropped an object from 1 meter above it, the object would hit the ground at millions of kilometers per hour. A place where a teaspoon of matter weighs as much as a mountain range. A neutron star. These objects shouldn't exist according to everyday logic. But the universe doesn't care about what seems reasonable. It cares about what the laws of physics allow. And physics allows this when a massive star exhausts its fuel and collapses the core, can compress into a ball of neutrons roughly 20 kilometers across, containing more mass than the sun. That's not metaphor. That's measurement. The journey begins with a supernova, when a star at least 8 times the mass of the sun runs out of nuclear fuel fusion stops. The core, no longer supported by the outward pressure of fusion, collapses in less than a second. Electrons are forced into protons, creating neutrons and releasing an enormous burst of neutrinos. The core rebounds, sending a shockwave outward that tears the star apart. What remains at the center is a neutron star. The density is almost unimaginable. Take all the mass of our sun, about 333,000 times Earth's mass, and compress it into a sphere the size of Manhattan. A sugar cube-sized chunk of neutron star material would weigh about 100 million tons. If you could somehow bring that sugar cube to Earth, it would punch through the planet's crust and fall toward the core. The atoms you're familiar with are mostly empty space. The nucleus occupies a tiny fraction of an atom's volume. In a neutron star, that empty space is gone. Neutrons are packed together as tightly as physics allows, forming something called neutron degenerate matter. It's one step away from collapsing into a black hole. The surface is solid, probably. Physicists think neutron stars have crusts made of iron nuclei arranged in crystal lattices, with a sea of electrons flowing between them. Below that, the nuclei become more exotic shapes that don't exist anywhere else in the universe. Rods, sheets, structures nicknamed nuclear pasta because of their resemblance to spaghetti and lasagna. Deeper still, neutrons become a superfluid, a quantum state of matter with zero viscosity. And at the very core, no one knows for sure. The pressure is so extreme that neutrons might break down into quarks, forming something called quark matter. But we can't test this. We can't recreate those conditions in a laboratory. Neutron stars are natural experiments physics can't replicate. Some neutron stars spin fast. When the core of a star collapses, it conserves angular momentum, the same way a figure skater spins faster when they pull their arms in. A star that was rotating once every few weeks compresses into a sphere 20 kilometers wide and suddenly spins hundreds of times per second. The fastest known pulsar, PSR J17246AD, rotates 716 times per second. That's 43,000 revolutions per minute. The surface of this neutron star is moving at roughly 25% the speed of light. If it spun any faster, it would tear itself apart. These rapidly spinning neutron stars emit beams of radiation from their magnetic poles. As the star rotates, the beams sweep across space like lighthouse beams. When one of those beams points toward Earth, we detect a pulse of radio waves. That's why we call them pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge. She was analyzing radio telescope data when she noticed something extraordinary, a signal that repeated every 1.337 seconds, precise as clockwork. Nothing natural they'd ever observed behaved like that. For a brief moment, the research team wondered if they had detected an alien signal. They half-jokingly nicknamed it LGM-1, Little Green Men. But soon they found more pulsars scattered across the sky, all with slightly different periods. The explanation wasn't aliens. It was something equally remarkable. Dead stars spinning in the dark, broadcasting their existence across the galaxy. Pulsars are extraordinarily precise. Millisecond pulsars, neutron stars spinning hundreds of times per second, are more stable than atomic clocks. Some deviate by less than a microsecond over decades. Astronomers use them as cosmic timekeepers, natural clocks scattered throughout the Milky Way. In 1974, astronomers Russell Holtz and Joe Taylor discovered something even more remarkable, a binary pulsar system. Two neutron stars orbiting each other, one of them a pulsar. By tracking the pulsar signal over time, they could measure the orbit with incredible precision. They found the orbit was slowly decaying. The two neutron stars were spiraling toward each other, losing orbital energy. Where was the energy going? Into gravitational waves. Einstein's general relativity predicts that accelerating masses produce ripples in space-time gravitational waves that carry energy away from the system. Holtz and Taylor's measurements matched Einstein's predictions almost exactly. It was the first indirect evidence that gravitational waves exist. They won the Nobel Prize in 1993. In 2017, astronomers detected something unprecedented: gravitational waves from two neutron stars colliding 130 million light-years away. The collision was so violent, it produced gravitational waves strong enough to detect on Earth using LIGO, the Laser Interferometer Gravitational Wave Observatory. But that wasn't all. About 2 seconds after the gravitational wave signal, gamma-ray telescopes detected a burst of high-energy radiation from the same location. Then hours later, Optical telescopes saw a glow, a kilonova, an explosion hundreds of times brighter than a typical supernova. For the first time, humanity observed a cosmic event with both gravitational waves and light. Multiple observatories around the world watched the collision's aftermath, studying the light as it faded over days and weeks. Spectra revealed signatures of heavy elements: gold, platinum, uranium. Neutron star collisions forged the heaviest elements in the periodic table. The gold in your jewelry, the platinum in electronics, the uranium in nuclear reactors, all of it was created in collisions like this. When neutron stars merge, the extreme heat and pressure allow rapid neutron capture, building elements heavier than iron. Those elements are scattered into space, mixing with interstellar gas, eventually forming new stars and planets. You're wearing atoms forged in the collision of dead stars. Neutron stars also have the strongest magnetic fields in the universe, millions to billions of times stronger than Earth's. Some neutron stars, called magnetars, have fields so intense they warp the quantum vacuum around them. If you got within 1,000 kilometers of a magnetar, its magnetic field would disrupt the electromagnetic bonds holding atoms together. You'd dissolve, not from heat or gravity, from magnetism. In 2004, astronomers detected a giant flare from magnetar SGR 1806-20, located 50,000 light-years away. The burst of energy was so intense it affected Earth's ionosphere, the upper layer of our atmosphere. A stellar explosion halfway across the galaxy changed Earth's atmosphere for a few minutes. Neutron stars remind us that the universe contains extremes we can barely comprehend. Places where a teaspoon weighs 1 billion tons, where stars spin 700 times per second, where magnetic fields can tear apart atoms, where collisions create gold. They're the densest objects in the universe that aren't black holes, the boundary between matter and collapse, the edge of what's possible before space-time gives up and curves inward forever. And they're real, spinning quietly in the dark, keeping time, forging elements, warping space-time around them like stones in a stretched fabric. Somewhere in the Milky Way, a neutron star just completed another rotation. It took less than 2 milliseconds. Space isn't empty. It's a fabric. You can stretch it, compress it, send ripples through it like waves across water. When massive objects accelerate, when black holes spiral together, when neutron stars collide, they shake space-time itself, creating waves that travel outward at the speed of light. Gravitational waves. Einstein predicted them in 1916, just months after publishing general relativity. His equation showed that accelerating masses should produce ripples in the curvature of space-time, carrying energy away from the source. But Einstein himself doubted they'd ever be detected. He calculated how faint they'd be. Unimaginably faint. A gravitational wave passing through Earth stretches and compresses space by less than 1/10,000th the width of a proton. Imagine trying to measure a change in the distance between Earth and the Sun that's smaller than the width of a single atom. That's the scale of the challenge. For decades, most physicists thought direct detection was impossible. But on September 14, 2015, at 5:51 a.m. Eastern Time, 2 detectors in the United States, one in Louisiana, one in Washington State, recorded something extraordinary. A signal that matched the predicted waveform of 2 black holes spiraling together and merging 1.3 billion light-years away. LIGO. The Laser Interferometer Gravitational Wave Observatory had detected gravitational waves for the first time in history. The signal lasted less than 1/4 of a second. But in that brief moment, scientists could extract an astonishing amount of information. The 2 black holes weighed about 29 and 36 solar masses. They had been orbiting each other for millions of years, gradually spiraling inward as they lost energy to gravitational radiation. In the final fraction of a second, they merged, creating a single black hole of 62 solar masses. Wait, 29 plus 36 equals 65, not 62. 3 solar masses more than 600 times the mass of Earth were converted directly into gravitational wave energy. Einstein's equation, EMC2, in its purest form, mass became energy. Energy became ripples in space-time. Those ripples crossed 1.3 billion light-years of emptiness and arrived at Earth shaking 2 detectors separated by 1/800 miles. You can hear the collision. LIGO scientists converted the gravitational wave signal into sound frequencies humans can hear. It sounds like a chirp, a rising tone that sweeps upward and ends abruptly. The pitch rises because the black holes orbit faster and faster as they spiral inward, emitting gravitational waves at higher frequencies until they merge. It's the sound of space-time, ringing like a bell. How does LIGO work? Each detector is shaped like a giant L with arms 4 kilometers long. A laser beam is split and sent down both arms, then reflected back by mirrors at the ends. When the beams recombine, they create an interference pattern. If a gravitational wave passes through it, stretches space in one direction and compresses it in the other, the arm lengths change by an infinitesimal amount, far less than the width of a proton, but enough to shift the interference pattern. The precision required is staggering. LIGO can detect a change in arm length of about 10-18 meters, a thousandth the width of a proton. To put that in perspective, if the distance between Earth and the nearest star were scaled down to the width of a human hair, LIGO could detect a change in that distance smaller than the width of an atom. Everything tries to interfere with the measurement. Earthquakes, passing trucks, ocean waves crashing on distant shores. Even the quantum jitter of photons in the laser beam itself creates noise. LIGO filters out all of it, searching for the specific pattern of a gravitational wave. On that September morning in 2015, the signal was clear enough that researchers saw it almost immediately. Some thought it was a test signal injected into the data to train the detection algorithms, but it wasn't. It was real. Space-time had spoken. Since that first detection, LIGO and its partner observatory Virgo, located in Italy, have detected dozens of gravitational wave events. Most are black hole mergers. A few are neutron star collisions. Each one teaches us something new about the universe. In August 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars merging about 130 million light-years away. This event was different because neutron stars emit light. About 2 seconds after the gravitational wave signal, gamma-ray telescopes detected a short burst of high-energy radiation from the same patch of sky. Then, hours later, optical telescopes found the source, a new point of light in galaxy NGC 4993. Astronomers watched the kilonova evolve over days and weeks, studying the light to understand what elements were being created. Spectra revealed gold, platinum, and other heavy elements, proof that neutron star collisions forged the heaviest atoms in the periodic table. For the first time, humanity observed a cosmic event through both gravitational waves and light. Astronomers called it multi-messenger astronomy, using different types of signals to study the same event, like watching a lightning storm, with both your eyes and your ears. Gravitational waves carry information, light can't. Light can be absorbed or scattered. Gravitational waves pass through matter almost entirely unaffected. They carry information directly from the source, unaltered by anything in between. When 2 black holes merge deep inside a dusty galaxy, you might not see any light. But the gravitational waves reach you unchanged. They also let us see further back in time than light ever could. The cosmic microwave background, the oldest light in the universe, comes from 380,000 years after the Big Bang. Before that, the universe was opaque to light. But gravitational waves from the early universe, if they exist, would travel freely through that opaque plasma. Detecting primordial gravitational waves would let us see the universe as it was in the first fraction of a second after the Big Bang. Several experiments are searching for this signal. Einstein's equations describe gravity not as a force, but as the curvature of space-time. Mass tells space-time how to curve. Space-time tells mass how to move. Gravitational waves are the dynamic proof of this relationship curvature itself, rippling outward, carrying energy, reshaping space as they pass. You're moving through ripples right now. Gravitational waves from distant collisions are passing through your body constantly. They're too weak to detect without instruments like LIGO, but they're real. Every few seconds, somewhere in the universe, two black holes merge. Every few minutes, two neutron stars collide. Each event sends gravitational waves racing outward in all directions. Space itself is alive with vibrations too small to feel. In the 2030s, the European Space Agency plans to launch LISA, the Laser Interferometer Space Antenna. Unlike LIGO, which detects high-frequency gravitational waves from stellar mass black holes, LISA will detect low-frequency waves from supermassive black holes, millions or billions of times heavier than the Sun. LISA will consist of 3 spacecraft arranged in a triangle separated by 2.5 million kilometers. Lasers will measure the distances between them, detecting the tiny stretches and compressions caused by gravitational waves. Free from Earth's seismic noise, floating in the quiet of space, LISA will hear the universe breathing. Collisions between supermassive black holes, binary star systems throughout the Milky Way, perhaps even signals from the Big Bang itself. Gravitational wave astronomy is still young. LIGO's first detection was less than a decade ago. We're just beginning to listen. Every new detection reveals something unexpected. Black holes heavier than we thought possible. Neutron stars lighter than our models, predicted merger rates different than calculated. The universe keeps surprising us. Somewhere out there, 2 massive objects are orbiting each other, spiraling closer, warping space-time around them. Eventually, they'll merge. The collision will send ripples racing outward at the speed of light, carrying the energy of suns converted into pure geometry. And maybe, if we're listening, we'll hear it. What if this universe isn't the only one? What if every choice you've ever made created a branch, a split in reality, where another version of you made the opposite decision? What if the Big Bang that created our cosmos was just one bubble in an infinite foam of universes, each with different laws of physics, different constants, different outcomes? It sounds like science fiction, but some physicists take it seriously. The multiverse isn't a single idea. It's a collection of possibilities that emerge from different areas of physics. Some come from quantum mechanics, some from cosmology, some from string theory. They all point toward the same unsettling conclusion: the universe you see might be one of many, maybe infinitely many. The simplest version comes from quantum mechanics. In the 1920s, physicists discovered that particles don't have definite properties until you measure them. An electron doesn't have a specific position or momentum. It exists in a superposition of all possible states simultaneously. Only when you observe it does the wave function collapse and the particle takes on a definite value. But why does it collapse? In 1957, physicist Hugh Everett proposed a radical answer: it doesn't. The wave function never collapses. Instead, every possible outcome of a quantum measurement actually happens. When you measure an electron's position, the universe splits. In one branch, you find the electron here. In another branch, you find it there. Both versions of you exist each in a separate universe, unaware of the other. This is the many worlds interpretation. It's not as wild as it sounds. Everett was trying to solve a genuine problem in quantum mechanics. If you take the math seriously, if you follow the equations without imposing an arbitrary collapse, multiple outcomes naturally emerge. The splitting isn't something added to the theory. It's what the equations predict when you let them run without interference. Every quantum event creates branches. Every particle interaction, every photon absorbed, every atom decaying. The universe splits constantly, endlessly into versions that differ by microscopic quantum events. You exist in trillions of parallel worlds, each one slightly different. In one universe, you sneezed 5 seconds ago. In another, you didn't. In another, you never started reading this. In another, you don't exist because a cosmic ray struck a different DNA molecule in one of your ancestors. Most branches differ only in tiny quantum scale ways. But over time, those differences compound. Some physicists love many worlds because it's mathematically clean. No collapse, no special role for observers, just the equations unfolding. Others hate it because it's untestable. If the branches can't interact, you can never prove the other universes exist. But there's another kind of multiverse. Eternal inflation. Our universe began with the Big Bang, a period of rapid expansion that smoothed space and set the stage for galaxies and stars. But inflation theory developed in the 1980s by physicists like Alan Guth and Andre Linde suggests that inflation might not have stopped everywhere at once. In most regions, inflation ended. Space stopped expanding exponentially, cooled down, and allowed matter to form. That's our observable universe. But beyond the cosmic horizon and regions, we can't see inflation might still be happening. And in those regions, new pocket universes constantly bubble off each one, expanding and cooling into a separate cosmos. Imagine a pot of boiling water. Bubbles form, grow separate. Each bubble is a universe. Our universe is one bubble. Beyond our cosmic horizon, the pot is still boiling, creating new bubbles forever. Eternal inflation creates an infinite number of universes, each one causally disconnected from the others. You can't travel between them. Light from one can't reach another. They're separate realities born from the same underlying inflationary field. And here's the strange part. If there are infinitely many universes and quantum mechanics allows for all possible arrangements of matter, then every possible configuration must exist somewhere. There's a universe where you made every possible choice. A universe where dinosaurs never went extinct. A universe where Earth formed with 3 moons. A universe identical to ours except one atom is displaced by a nanometer. Infinity is exhaustive. String theory adds yet another layer. If string theory is correct, if the fundamental building blocks of reality are tiny, vibrating strings rather than point particles, then the equations allow for many different vacuum states. Each vacuum state corresponds to a different set of physical laws. Different particle masses, different force strengths, different dimensions of space. Physicists call this the landscape of vast space of possible universes, each one stable, each one with its own physics. Some estimates suggest there might be 10 to 500 different vacuum states. That's more universes than there are atoms in our observable cosmos. Most of those universes would be unrecognizable. In some, electrons are too heavy for atoms to form. In others, gravity is so strong that stars collapse immediately. In others, the electromagnetic force is too weak for chemistry to happen. Most universes are sterile, lifeless, boring. We exist in one of the rare universes where the constants happen to allow complexity. This raises an uncomfortable question. Why? Why are the laws of physics in our universe so finely tuned for life? The strength of gravity, the mass of the electron, the charge of the proton. If any of these constants were even slightly different, stars wouldn't form, atoms wouldn't bond, chemistry wouldn't happen. The universe would be a featureless soup of particles, or it would have collapsed immediately. Or it would have expanded so fast that matter never clumped together. Some people say this proves design, others say it's just luck. But the multiverse offers a third answer, anthropic selection. If there are countless universes with different physical laws, we obviously exist in one, where the laws permit our existence. It's not surprising, it's inevitable. The universes where life is impossible have no one to observe them. We find ourselves in a life-permitting universe for the same reason fish find themselves in water. Not because water was designed for fish, but because fish exist where water exists. The fine-tuning isn't evidence of a creator. It's evidence of a vast cosmic lottery where countless universes exist, and we happen to be in one of the winning tickets. But can we ever test this maybe? Some versions of eternal inflation predict subtle patterns in the cosmic microwave background, faint circles or irregularities caused by our universe colliding with another bubble universe in the distant past. So far, no one has found convincing evidence. But scientists keep looking. If we ever detect signs of another universe, it would be one of the most profound discoveries in history. Proof that reality is far larger than we imagined. That our cosmos, with its 100 billion galaxies, each containing hundreds of billions of stars, is just one small bubble in an infinite foam. Or maybe we'll never know. Maybe the multiverse is real, but forever beyond our reach. Maybe every other universe is separated from ours by barriers we can never cross, distances. We can never measure dimensions we can never access. Maybe you'll live your entire life in this universe unaware of the countless others, where different versions of you made different choices. Some physicists argue the multiverse isn't science because it can't be tested. If you can't observe it, they say it's not physics, it's philosophy. Others argue that if a well-tested theory predicts multiple universes as a natural consequence, we should take that prediction seriously, even if we can't visit them. The debate continues, but here's what's certain: the universe you see, the stars, the galaxies, the light traveling toward you from billions of years ago, is real, vast, ancient, full of mysteries we're only beginning to understand. Whether it's the only universe or one of infinitely many doesn't change the fact that it's here, and so are you. In this universe, in this moment, looking up at a sky full of questions. Stars don't live forever. They're born in clouds of gas and dust scattered throughout the galaxy. Gravity pulls the cloud together, slowly at first, then faster. Atoms collide, pressure builds, temperature rises. Eventually, the core gets hot enough around 10 million degrees Celsius for nuclear fusion to ignite. Hydrogen atoms slam together, forming helium, releasing tremendous energy. A star is born. Our sun formed about 4.6 billion years ago from a collapsing cloud of gas left over from previous generations of stars. That cloud contained hydrogen and helium from the Big Bang, but also heavier elements. Carbon, oxygen, iron forged inside ancient stars that lived, died, and scattered their remains into space. Every atom in your body heavier than hydrogen was made inside a star. Carl Sagan famously said, "We are made of star stuff." He wasn't speaking poetically. He was being literal. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized inside stellar cores through nuclear fusion, then released into the galaxy when those stars died. You're built from the ashes of dead stars. Stars spend most of their lives fusing hydrogen into helium in their cores. This is called the main sequence phase. For stars like the Sun, this phase lasts about 10 billion years. Larger stars burn faster and die younger. Some live only a few million years. Smaller stars burn slowly and can live for trillions of years, far longer than the current age of the universe. Mass determines fate. When a star exhausts the hydrogen in its core, fusion stops. Without the outward pressure from fusion, gravity starts winning. The core contracts and heats up. Eventually, it gets hot enough to fuse helium into carbon and oxygen. The outer layers expand dramatically, and the star becomes a red giant. Our sun will do this in about 5 billion years. It will swell until it engulfs Mercury, Venus, and possibly Earth. The surface will cool, glowing red instead of yellow, but the core will burn hotter than ever, fusing helium into heavier elements. For a few 100 million years, the sun will be a giant, hundreds of times its current size, casting faint red light across whatever's left of the solar system. Then the outer layers drift away. Without enough mass to compress the core, further fusion stops. The outer envelope gently disperses into space, forming a planetary nebula, glowing shells of gas lit by the ultraviolet radiation from the exposed core. The core itself becomes a white dwarf, a sphere about the size of Earth, made of carbon and oxygen, no longer fusing, just radiating away its residual heat. White dwarfs are dense. A teaspoon of white dwarf material weighs about 5 tons. The atoms are packed so tightly that electrons can't get any closer, a quantum mechanical effect called electron degeneracy pressure. This pressure holds the white dwarf up against gravity. It will cool slowly over trillions of years, fading from white to yellow to red to black, becoming a cold, dark cinder floating through space. A black dwarf. Though the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still faintly glowing, but larger stars die differently. If a star is more than about 8 times the sun's mass, it can fuse elements beyond helium. Carbon fuses into neon and magnesium. Neon fuses into oxygen. Oxygen into silicon. Silicon into iron. Each stage requires higher temperatures and lasts for a shorter time. A massive star might spend millions of years fusing hydrogen, but only days fusing silicon into iron. Iron is the end. Fusing iron consumes energy instead of releasing it. Once the core fills with iron, fusion stops. There's no energy source left to hold the star up. The core, now about the mass of the sun, but compressed into a sphere the size of Earth, collapses in less than a second. The collapse is catastrophic. Electrons are forced into protons, forming neutrons and releasing a flood of neutrinos. The core rebounds, sending a shock wave outward that tears the star apart. The outer layers explode into space at speeds of tens of thousands of kilometers per second. A supernova? For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion scatters elements across space: oxygen, carbon, iron, gold, seeding the interstellar medium with the raw materials for new stars and planets. All the heavy elements in the universe were made inside stars or during their explosive deaths. The gold in your jewelry was forged in a supernova or a neutron star collision. The oxygen you just inhaled was created in a dying star billions of years ago. The silicon in the microchips in your phone, the calcium in your bones, the iron in your blood, all products of stellar nucleosynthesis. You exist because stars died. What's left after a supernova depends on the core's mass. If the core is between about 1.4 and 3 solar masses, electron degeneracy pressure fails, but neutron degeneracy pressure holds. The core becomes a neutron star, a sphere 20 kilometers across, weighing more than the sun, spinning rapidly, and emitting beams of radiation. If the core is more than about 3 solar masses, nothing can stop the collapse. Not electrons, not neutrons. The core compresses past every known limit, shrinking until it becomes a black hole, a region of space-time so warped that not even light can escape. The most massive stars leave behind the densest objects in the universe. But there's another path. Some stars don't explode. If a white dwarf is in a binary system with another star, it can pull matter from its companion. The material spirals onto the white dwarf's surface, gradually increasing its mass. If the white dwarf reaches about 1.4 solar masses, the Chandrasekhar limit electron degeneracy pressure fails. The entire star collapses and undergoes runaway fusion all at once. A type Ia supernova. These explosions are incredibly consistent. Because they always happen at the same mass, they always release roughly the same amount of energy. Astronomers use them as standard candles to measure cosmic distances. Type Ia supernovae are how we discovered that the universe's expansion is accelerating, driven by dark energy. Even in death, stars teach us about the cosmos. The most massive stars, over 100 solar masses, die in a different way. They're so luminous that radiation pressure pushes material away from the surface, creating powerful stellar winds. These stars can lose half their mass before they die. When they finally explode, they might produce a hypernova or collapse directly into a black hole without a visible explosion. Some of the universe's first stars might have been this massive. Population the 3 stars, formed from pure hydrogen and helium, with no heavy elements, could have grown to hundreds of solar masses. They burn bright and fast, living just a few million years before exploding and seeding the cosmos with the first metals. Every generation of stars builds on the ashes of the previous generation. The Sun is a 3rd-generation star, at least. It formed from material enriched by 2 earlier generations of stars that lived, fused elements, died, and scattered those elements into space. When the Sun eventually becomes a white dwarf, its carbon and oxygen will drift through the galaxy. Billions of years later, that material might be incorporated into a new star, or a planet, or even a living being. The cycle continues. Stars are forges. Fusion reactors that transform simple hydrogen into the complex elements that make up planet's life and everything you see around you. They live for millions or billions of years, then die, some gently, some violently, returning their enriched material to the galaxy. The iron and hemoglobin that carries oxygen through your bloodstream was created inside a massive star more than 4.6 billion years ago. That star lived its life, exhausted its fuel, and exploded, scattering iron atoms into a cloud of gas. That cloud collapsed, forming the Sun and planets. One of those planets developed an atmosphere, oceans, and eventually life. And now some of those iron atoms are inside you, essential to your existence. You're not separate from the universe. You're continuous with it. Every breath contains atoms that once belonged to dinosaurs, oceans, distant stars. Every element in your body connects you to cosmic history, spanning billions of years. The universe isn't something you observe from the outside. You're part of its story, a brief arrangement of stardust that can think, feel, and wonder where it came from. Stars die so that others can live. Everything ends, not with fire, not with explosion, not with a cosmic collapse that reverses time and squeezes the universe back into a point. The most likely ending is gentler than that, slower, quieter. The universe will simply cool down. Stars will burn out one by one. Galaxies will drift apart, carried by the accelerating expansion of space. Light will stretch into wavelengths too long to detect. Eventually, after an unimaginably long time, every source of energy will be exhausted. The universe will reach maximum entropy, a state of perfect equilibrium where nothing can happen anymore. Physicists call it heat death, not because the universe gets hot, because it gets cold, uniformly cold, a temperature barely above absolute zero, spread evenly across infinite space, with no differences, no gradients, no way to extract useful energy from anything. This is what the second law of thermodynamics predicts. Entropy always increases in a closed system. Energy spreads out. Hot things cool down. Ordered structures decay into disorder. You can't unscramble an egg. You can't unmix cream from coffee. The universe as a whole is moving toward a state of maximum entropy, where all differences have been smoothed out, and nothing interesting can happen anymore. It's not happening soon. The timeline for heat death is so long, it's hard to grasp. We measure it not in billions of years, but in durations that make billions of years seem like the blink of an eye. The universe is currently 13.8 billion years old. Heat death won't arrive for at least 10⁻100 years. That's a 1 followed by 100 zeros. To put that in perspective, there have been about 10^18 seconds since the Big Bang. Heat death is 1082 times further in the future than the Big Bang is in the past. But it's the most probable fate. Cosmologists recognize a few possible endings for the universe depending on the balance between expansion and gravity. If there's enough matter to eventually stop the expansion, the universe could reverse and collapse into a big crunch. If dark energy behaves differently than expected, the universe could be torn apart in a big rip. But current observations suggest neither of these will happen. Dark energy is accelerating the expansion. Galaxies beyond our local group are moving away faster and faster. In a few trillion years, they'll be so far away that their light will never reach us. Future civilizations, if they exist, will look into the sky and see only their own galaxy surrounded by darkness. They might not even know other galaxies exist. The first things to go will be the stars. Stars form from clouds of hydrogen and helium, but there's only so much gas available. Every generation of stars uses up some of that material, locking it into stellar remnants. White dwarfs, neutron stars, black holes. Eventually, around 100 trillion years from now, the last star will form. A few trillion years after that, the last star will die. The stelliferous era, the age of stars, will end. What's left will be a universe full of dead objects. White dwarfs cooling into black dwarfs. Neutron stars spinning silently. Black holes drifting through empty space. No fusion, no light. Just gravity and darkness. But even that's not the end. On timescales of 1030 to 1040 years, something strange happens. Stars, planets, and other objects in galaxies occasionally have close gravitational encounters. Most of these encounters result in objects being flung out of galaxies into intergalactic space. Over unimaginable stretches of time, galaxies evaporate their constituent objects scattered across the universe. Black holes grow. Any matter that doesn't escape eventually falls into the central black hole of a galaxy. Over 10-20 years or so, most galaxies will be reduced to a single supermassive black hole surrounded by vast emptiness. But black holes don't last forever either. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. It's incredibly faint. A black hole with the mass of the sun radiates at a temperature of 60 billionths of a Kelvin, far colder than the cosmic microwave background. It would take about 1,067 years for such a black hole to evaporate completely. Supermassive black holes take even longer. A black hole with 1 billion solar masses would take 1,098 years to evaporate. But eventually, even the largest black holes will radiate away their mass one particle at a time until nothing remains. This is the black hole era. After 100 years, even black holes are gone. What's left is a universe filled with a thin soup of photons, neutrinos, and occasional electrons and positrons, all spread across an expanding space that's grown incomprehensibly large. The temperature everywhere is a fraction of a degree above absolute zero. This is the dark era, the final state. In this era, the universe is dark cold and essentially empty. Particles are so spread out that encounters between them are extraordinarily rare. The cosmos has reached maximum entropy. There's no free energy left to do work. No stars can form. No chemistry can happen. No complexity can arise. Time still passes, but nothing changes. Some physicists wonder if even this isn't quite the end. Quantum mechanics suggests that extremely rare fluctuations could occur, random arrangements of particles that momentarily decrease entropy in a tiny region. Over time scales of 10 years or more, these fluctuations could theoretically produce anything, including brains that spontaneously assemble and exist for a brief moment before dissolving back into chaos. These are called Boltzmann brains. The idea is unsettling. If the universe lasts forever, and rare quantum fluctuations can produce consciousness, then most conscious observers in the history of the universe would be these isolated, randomly assembled brains, not evolved beings like us. It's a paradox cosmologists take seriously, and it places constraints on theories of the far future. But whether or not Boltzmann brains exist, the underlying point remains. The universe is heading toward a state where nothing complex or organized can persist. You might find this depressing. The idea that everything stars galaxies' life, consciousness, every thought anyone has ever had, will eventually dissipate into cold, dark equilibrium can feel nihilistic. If everything ends, does anything matter? But maybe it's the opposite. The universe is heading toward heat death. Yes. but that's trillions upon trillions of years away. Right now, you're alive in the most interesting era the universe will ever have. Stars are shining, galaxies are forming, planets orbit suns, life has emerged, consciousness has arisen. Beings made of stardust can look up wonder and understand. This moment is rare. The universe spent its first few 100 million years as a dark cooling plasma. It will spend its last 100 years as a cold, empty void. But in between right now, in this brief window of cosmic time, the universe is full of light structure and possibility. You exist during the most luminous age the cosmos will ever know. Heat death is inevitable, but it's not a reason for despair. It's a reminder that existence is temporary, that the stars won't shine forever, that the time you have, the time we all have, is precious precisely because it's finite. The universe will end in silence, but before it does, it produces galaxies, stars, planets, life, and minds capable of understanding their own impermanence. That's not tragic. That's remarkable. Everything ends, but not yet. For now, there are stars in the sky, light traveling across space, atoms arranged into forms complex enough to think and feel and wonder. The universe is still young enough to be interesting, and you're here to see it. We've traveled far tonight, through light that remembers where it's been, through invisible matter holding galaxies together, through the oldest glow in existence carried across 13.8 billion years, through space that bends and stretches, creating distance where none existed before. We've watched black holes warp time itself, listened to neutron stars spinning faster than thought, felt gravitational waves ripple through the fabric of reality, wondered if other universes exist beyond the one we know. We've seen how stars are born from clouds live for billions of years, then scatter their atoms into space so new stars can form. We've traced the calcium in your bones back to stellar cores. We've followed the universe forward to its quiet, distant ending. And here we are, still here, in this moment. The universe is vast, older than comprehension, larger than imagination, but you're part of it. Not separate, not observing from outside. You're woven into the same fabric that holds galaxies together, made from the same atoms that once burned inside stars. Every breath connects you to cosmic history. The oxygen you just inhaled was created inside a massive star that exploded billions of years ago. The carbon in your cells was forged through fusion in a stellar core. The iron in your blood formed in a supernova that scattered its remains across the galaxy, eventually becoming part of the dust cloud that collapsed into our sun and planets. You're not made of matter that came from the universe. You are the universe briefly arranged into a form that can wonder about itself. Science doesn't diminish that. It deepens it. Knowing that stars die doesn't make them less beautiful. Understanding how elements form doesn't make life less precious. Learning that the universe will eventually cool into darkness doesn't erase the fact that right now at this moment, you exist in an era of light and structure and possibility. You're alive during the most interesting chapter of cosmic history. The universe spent hundreds of millions of years as dark plasma cooling in silence. It will spend incomprehensibly long ages as a cold, empty void. But between those epochs, right now, stars shine. Galaxies spiral. Planets orbit suns. Consciousness arises. This window won't last forever. But it's happening now. And somehow, against odds that seem impossible, atoms arrange themselves into eyes that can see starlight, into minds that can understand gravity, decode the cosmic microwave background, detect gravitational waves from collisions a billion light years away. The universe made tools to study itself, and you're one of them. Tonight, we walk through knowledge that took centuries to gather. Galileo pointed a telescope at Jupiter and saw moons orbiting something other than Earth. Hubble measured galaxies receding and realized space itself was expanding. Rubin discovered invisible matter holding galaxies together. Penzias and Wilson found ancient light by accident. Each discovery revealed something unexpected. Each answer raised new questions. The universe doesn't owe us understanding, but it offers clues, patterns in starlight, ripples in space-time, equations that describe how matter bends geometry. Every observation is a conversation between human curiosity and cosmic reality. We're still learning the language. There's so much we don't know. What dark matter is made of, whether other universes exist, what happens inside black holes, how the first stars formed, why the laws of physics have the values they do. Maybe we'll find answers. Maybe some questions will remain mysteries forever. But not knowing doesn't diminish the wonder, it deepens it. The universe doesn't need to be fully understood to be appreciated. You don't need to grasp every detail to feel connected to something larger than yourself. The fact that photons from distant stars enter your eyes and trigger cascades of chemical reactions that become thoughts that alone is extraordinary. You're stardust contemplating stars. Some nights when you look up, you might feel small. The universe is so vast and human, lifespans are so brief. 100 years against 13.8 billion. A single planet in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. But size isn't significance. You're not less important because the universe is large. You're part of the process that allows the universe to know itself. Consciousness is rare. The ability to wonder, to question, to understand, that's not trivial. That's remarkable. And you're here, aware, thinking, feeling the quiet weight of existence. Tonight you've rested while learning. Let your mind drift through concepts that usually feel too large to hold. Gravitational waves and neutron stars and the slow cooling of everything. Maybe some of it will stay with you. Maybe you'll look at the night sky differently now, knowing that the light reaching your eyes left those stars years or centuries or millennia ago. Knowing that invisible matter surrounds you. Knowing that space itself is expanding, carrying distant galaxies beyond the edge of what we'll ever see. Or maybe you'll simply sleep, and that's enough. Knowledge doesn't demand anything from you. It's just there waiting quietly, like starlight crossing empty space. You can reach for it when you're ready, or let it pass by content to exist without needing to understand everything. The universe will keep unfolding, whether you're paying attention or not. But tonight you listened. You traveled through time and space without leaving your room. You touched the edge of human knowledge and felt the questions that remain unanswered. That's enough. Rest now. Let the thoughts settle like dust. Let your breathing slow. Let the universe continue its quiet work, expanding, cooling, spinning, creating, while you drift into sleep. You've seen enough for one night. The stars will still be there tomorrow. The galaxies will keep turning. Space will keep stretching. And you'll wake up in a universe that's slightly older, slightly larger, still full of mysteries. But for now, let go. Sleep well, dream gently. Good night.